we are still working on solving the tangent line problem. And I think we've done a good solution to it, right? Method one, right? We've used that to find the slopey tangent lines of quadratics, square roots, and fractions. Yeah, I don't like the fractions so much, they were ugly, but we could do it, right? And if you do it for f dashed of a, doesn't that give you the added benefit that once you've done it once, you can then just make a equals 2 or a equals 6, and you can get the slopes of the tangent line anywhere on that curve. And that is totally cool. And if you said to me which method between the two that we would use, I normally go this one. So you might or might not know that there's actually two methods. And we're going to start today by looking into this one. And then I'm going to show you an example of it. I'm just going to do one. I think I'll do a quadratic or a square root. Maybe I'll do two. Okay, talk myself out of it. I definitely won't do a fraction. And essentially what we're going to do here is set up the problem, but look at it just a slightly different way. So here's the curve, just like we always did. Here's the point A that we want to get the slope of the tangent line for. Here is the point Q. But we're not going to call this guy A plus H. I'm just going to call him X, where X could be any number I like, except A. It's not allowed to be A, but it can be any other number, right? And typically some number a little bit bigger than A, right? Now, if I wanted to find the slope of the secant line joining P to Q, which we all know is rise over run, I can basically say YQ, take away YP, XQ, take away XP. I mean, it's almost the same setup, right, as we did when we proved this thing, or when we got the equation for this thing. And the Y coordinate is this is f of X, take away f of A, and X, take away A. And so if I want to find the slope of the tangent line at A, we'll call it the derivative of A for short. What we do is this. We find the limit as X tends to A of this guy. Essentially, what would happen to the slope of the line joining P to Q if X tended towards A? Would you agree that would do the same job? Wouldn't that be the shrinking of the gap until there's almost no difference? So this here is our second method. Now, unless the homework specifically says use this method, I suggest strongly that we just stick to the first one. It works fine, and I just like it better. But I mean, if you take a look at this one and you suddenly think, no, this one works for my brain, I see it better, or the math is easier in my head, then I don't have any problems with using method 2 if you feel like it. But my experience is that method 1 is much simpler. So let's put it into action. Question?
If they want us to use method 2, they're not going to say use method 2. So what are they going to call it?
They're going to say use this.
Oh, they're going to give it to you.
Yeah.
Oh, okay.
For instance, question, it's either 1 or 3. Let me find it. Yeah, question 3A part 1 makes you use it. That's the only one I could see offhand. The rest of the time, they just say, you know, find the slope of the tangent line at 2 or find f dashed of 2, which case you're open to whatever you like. Okay, let's do a quadratic. 2x squared plus 3x minus 1. And let's just do that fella, right? You know, the f dashed of a one, which is essentially the slope of the tangent line at x equals a, right? So it's going to be the limit as x tends to a of f of x take away f of a over x minus a. And that's quite a different looking formula. Look, this one, you always go to 0, right? H always goes to 0, and this is the fraction that you're calculating. Here, X goes to A, and this is the fraction. So the math is going to look a little bit different because of that. So let's see what we get then. It's going to be the limit as X tends to A of f of X, which is 2x squared plus 3x take away 1, subtract f of A, which is 2a squared plus 3a take away 1, all over x minus a. And this is going to be the limit as x tends to a of 2x squared take away 2a squared plus 3x take away 3a. And won't that -1 kill off this guy? So that's all we've got left. So far, so good. Not an awful lot of cancelling, at least the numbers disappeared, which they always will. But what you're left with here is quite different. The top will always have X's and A's in it, right? When you did this fella here, didn't you reach a stage where the top just had H's in it in some kind? Now, here's the trick and why I personally don't like this method. It's just a personal taste is that I now have to factor the top. And it isn't a clear, obvious factor. It just isn't, right? And the way that you approach these ones when it's polynomials, which it is here, is different than when it's a square root. If it's a square root function, you'll use a conjugate. Actually, I'll do that next. And if it's a fraction, you'll probably go grey trying to make the algebra work. I mean, it's really, really ugly. So I wouldn't even attempt a fraction unless you paid me money. So I'm going to approach the problem of having to factor the numerator. I'm going to take the first two terms and I'm going to pull out a common factor of A. I'm going to take the second two terms and pull out a common factor of 3. Now, the next bit, it doesn't look yet like I'm actually factoring anything. It looks like I'm just pulling out common factors from some bits, but not all of them. Do you recognize x squared minus a squared? Couldn't I factor it?
Yeah, square factor.
So how about an x plus a, x minus a? You happy about that? Now you might say, well, where's all this leading? It's leading to this. Doesn't this first term have an x minus a in it? And doesn't this second term have an x minus a in it? So couldn't I pull out x minus a as a common factor? What will that leave? It'll leave 2 lots of x plus a, add 3. Do you see that I've now factored this thing? And in particular, do you notice that the factor that I've pulled out is x minus a? So when you do these questions, that's what your goal is to suck out an x minus a. Don't care what that is or how ugly that is. Just, live with that. Just figure a way of factoring out an x minus a. And the way I did it here is basically by collecting like terms and factoring them accordingly. So that means I could cancel. And what I'm left with is 2 lots of x plus a, add 3. No more fractions to worry about, right? They cancel. All I'm left with is this. Now, if you want to find the limit of x tends to a of this, just replace the x with a. 2a times 2 is 4. So you get 4a, add 3. There is your answer. Would you agree the math is quite different from how I would have approached that question if I did the h tends to 0 formula? I think it's significantly different. Now, since I've got that guy, if I wanted to know the slope of the tangent line at 3, wouldn't the answer just be 4 lots of 3 add 3, which is 15? And if I wanted to know the slope of the tangent line at 1, it'd be 4 lots of 1 add 3, which is 7. So once you know this formula, can't you find the slope of any tangent line to that curve that you like by just replacing the a by the x coordinate of the point you're interested in? Now, I've kind of been unselling this technique. For some of you, does that make more sense or easier to do than the h tends to 0? Just curious. Or does it look a little bit messier?
How did we simplify the a plus a?
We cancelled 1 on the bottom with 1 on the top. How did we get from here to here? Is that your question, Robin?
No, the next line down where it's
Right.
2a plus a.
Right, what I did here is I cancelled this x minus a factor with the bottom, and when they disappeared, the 2x plus a plus 3 was left. So that's what it gives written here.
And then
Once
he gave the x value gets to be an a at the end.
Yeah, and then
Yeah,
here
put the
that's
a.
what
I
I'm
put an
talking
x
about.
with a. Oh, okay. We've got
Since
the limit
x
as x tends
a,
to
you
a
have two
of
a's, right? So
this fella. You replace the x with a, and now you've got an a plus a, and then it becomes up. We good?
and that is
Yeah.
that HA on the side?
There's no h's. If any of my a's look like h's, I apologize.
Oh no, that's 4a.
Yes, it's 4a add 3. Sometimes my 4s look like 6s as well, I've been told. Okay, let's do one more. I'm not going to focus really much on this except to show you that you could do it this way. Let's do the square root of 2x plus 1. And let's find the general derivative f dashed of a. So it's going to be the limit as x tends to a of f of x, take away f of a over x minus a. Now, we've done them yesterday with the h tends to 0 method. So let's see what the math looks like when you have this fella. F of x is just this fella. What's f of a? What do I write down for f of a?
Square root of 2a plus 1.
Yeah, in a lot of ways, it's quite simple, isn't it? That part is, isn't it? You just replace the x's with a's, and that's you got f of a. Now, I hope we just have done enough of these limit questions with square roots to realize that this is a conjugate method. Would you agree? It's kind of screaming out, use the conjugate method, and it is. So it's going to be the square root of 2x plus 1 add the square root of 2a plus 1, top and bottom. Yeah. This technique of multiplying by special versions of 1 is quite versatile. Haven't we used it in lots of different ways? Here it's the conjugate method. Can you remember yesterday we took care of that really ugly fraction by using a kind of special version of 1 technique on that? It wasn't a conjugate, but it was still the special version of 1. Very helpful technique. So it's going to be the limit as x tends to a of x minus a, square root of this guy, plus the square root of that guy. That's the bottom. Nothing really happening here. Now, this guy times this guy. Can't we do the first guy squared, take away the second guy squared trick? If you square the first guy, you get that. Take away, if you square the second guy, you get that. Are you happy about this guy squared, take away that guy squared? We've seen that step enough. Do you notice I put the brackets around it to make sure that you remember to subtract the whole thing?
I have a question.
Yes.
Or I have a comment.
Yeah.
I just realized the importance of why you do the bottom first. And I have on like 50% of the problems I did, I got through and I forgot to do the bottom. And so I got
Oh, you
an
just had
answer.
the top floating there, but nothing on the bottom.
Because the top is so complicated, I would just get into it and do it.
And
And
then
then
forget about the
I'd have
rest.
an H on the bottom and I'd be done. And then I'd have the wrong answer. And then I was like, what the heck? And then I'd go back and go, oh, I forgot to do that again. So now I'm going to start doing that like you. I'm going to do the bottom first because the bottom is usually simpler. And then I just
Yeah, at the
think
bottom, you
that,
just write down what's there. You don't do anything to it.
yeah, so I'm going to start doing that now. I don't know if that'll help anybody else.
I'm sure it will. There's going to be some magic happening any moment now. 2x plus 1, take away 2a, take away a 1. What you're left with is 2x, take away 2a. Don't the ones cancel that? So when you do this method, you will reach a point where the top, the numerator, only has x's and a's in it, right? If you have a plus 3 left over, there's a problem, right? It shouldn't do that. We have to work on this. Any suggestions for what I could do to the numerator?
You could factor out a 2.
So I heard, I'll write it down. Oh, that was good, wasn't it? Factoring out a 2 did a really nice thing. Can you see where we're going next? You see it? Boom. Which means we are now left with the limit as x tends to a of 2 on the top and this guy on the bottom. But typically when you get to this stage here, don't you just replace, in this case, the x's with a's, right? You can just substitute. You don't need to worry about 0 over 0 happening. It's not going to happen there. So what does that get me? It gets me 2 on the top. 2x plus 1, well, if you replace the x with a, you get 2a plus 1. So I have the square root of 2a plus 1 plus the square root of 2a plus 1, right? Okay, let's look at style points. Can we make this thing pretty, or at least prettier? Okay, what should I do?
On the bottom, you can do 2a plus 1.
Agreed?
Yeah. Yes.
And sometimes you can do more. Sometimes you're pretty much finished. In this question, we can do more. What can we do next?
Divide the 2.
Remember to leave a 1 behind when everything disappears. And I would say that that's a pretty nice answer. I would not rationalize the denominator because I think it looks ugly, right? Very nice answer. So if you wanted to know the slope of the tangent line to this particular curve at x equals 1, wouldn't the answer be 1 over the square root of 3? If you wanted to know it at 42, it'd be 1 over the square root of 95. And pretty much for one piece of work, you can now find the slope of the tangent line to any curve at any point you like. Now, I didn't, because I have time issues and I just don't think it would actually help much. Couldn't I have done both these questions with an x tends to 4 first and then do an x times to a second? Couldn't I have done them that way? Like we did yesterday, we did numbers and then we did the a version, right? I think we've come to the point now, wouldn't you typically just do the a version anyway and then plug in whatever the number was later if you wanted? Because there's some questions where you're going to be asked to find the slope at 1, at 2, 7, and 10. If you gave me 4 guys like that to do you know I would find f dash of a first, and then it'd be easy to get the 4 answers. So think about that as a strategy for maybe doing some of the homework questions, that it might be just easier to find the f dash of a and then plug it in. And even if it only asks for one, it might be just good practice to do an f-a anyway, you know, and then just plug in the 7 or whatever the number happens to be. So I'm going to continue with 2 more things I want to show you. Next thing I want to show you is, oops, excuse me, how to find the equation of a tangent line. Okay, how to find the equation of a tangent line, right? And who shall I do it with? Yeah, let's do it with this one. So suppose you are given this fella, and you're being asked to find the equation of the tangent line at the point 2, 2, 4, 8, 7, 6, 13, at 2, 13. And there are a couple of homework questions where that's essentially what you're being asked to do. So I have a function, and I'm being asked to find the equation of the tangent line at one point. And can we pretend, I'm not saying this is the right guy, but can you pretend that the picture might look something like this? There's P. This would be the tangent line, right? I can't draw very well, but this would be the tangent line. And we want to get that guy, right? By the way, there's no way in the world the right answer is going to be 3x plus 7. I'm just putting that down as an example. If the answer to this is 3x plus 7, the class is finishing today, I'm away to buy some lottery tickets, because that's about the same amount probability that it would be, you know, that I nailed it.
Good, pick me a one up too.
Oh, well, yeah, but the one I get for you wouldn't win.
You're right. Okay.
And yeah, you're in a bad week, so you're not going to get that one. Oh, God. Where was it? This is cool stuff. Right, we got this fella. So I'm going to skip a line. First step 1, would be to find the slope of the tangent line. At x equals 2. Right. Even if they didn't ask you to find it, you have to find it anyway. Now, since I've already done the work here, isn't the slope of the tangent line 4a plus 3, right? So in this case, wouldn't the slope of the tangent line be 11? Are you happy about how I would get that? I would do whatever working I needed to do to get the answer, and boom, I get the slope, right? If it was the square root one, see if it was this one here, and you wanted to find the slope of the tangent line at 2, wouldn't you just plug it in here and you'd get, well, the slope would be 1 over root 5. Kind of ugly answer, but that would be the slope. That's step 1. Step 2. Use the coordinates of the point and the slope to get the equation of the tangent line. So we are going to bring back a piece of math. Oh, God, where would you do it? 94, I think you would do this. Can you remember that there's a formula for getting the equation of a line when you know a coordinate that it passes through and you know its slope? Can you remember that guy? Now I'm going to do this guy. I'm going to call him X1. I'm going to call him Y1. Obviously, I'm calling him M. For brownie points, anybody want to tell me the equation? I think it's called the point slope equation for a line.
Y equals mx plus b.
That is definitely correct, but that would only be used. Not this time, no. You would use that one, Cassandra, if you knew the slope and the y-intercept.
Okay.
But this is the other one. This is the one where you only know a random point, not a y-intercept. Anybody want to go for that one?
Would it be y2 minus y1 equals m times x2 minus x1?
Oops, sorry, x minus x1. Yes, it would be. Do you kind of sort of remember that now that you've seen it? You're going to use that for, I think, about 3 or 4 questions where you've been asked to find the equation of the tangent line. Right, you'll know the point because I'll tell you. Eventually, you'll know the slope because you'll find it. And you put the package together, you get this. So it's going to be y take away 13 equals, a slope of 11, x take away 2, and that becomes y minus 13 equals 11x take away 22, and that becomes y equals 11x, add 13 to both sides, shooting space, 9. Does that look reasonable equation? We could check it. Let's see if, because, you know, I'm not perfect, although I think I am. I know I'm not.
Wouldn't it be a -9 and not a plus?
You are right the minute you said it. I'm going to put that in and show you how we could do that. I'll do my mistake and then I'll do my fix. So we're going to go 2x squared plus 3x, take away 1, right? That's the original thing, right? I'm going to do a window. I'm only interested in, you know, the point round about an x coordinate of 2. So, you know, if I do a window from, I don't know, from 1 to 4, would you agree that covers the guy we're interested in? And then I'll just do, for the time being, a zoom to fit. And you get a pretty boring curve. Not much of a curve, it's almost linear. That's fine. I'm now going to type in y2 the wrong answer. The equation of the line is 11x, and I had plus 9. Now watch what happens when I graph it. Does that line look like a tangent line to this curve? Nope. Now I'll put in the fixed version. Does that look like a tangent line to you? So it's not difficult to check. In fact, isn't it nice that visually what we've been doing actually does work, doesn't it? Get you tangent lines, and the equation matches perfectly about here where the tangent line should happen. Any questions so far? Does this seem, this new technique, method 2, does the job as well? Method 1 does it. Pick whatever method you like to get the slope, and then you can do this part here, step 2, to get the equation of the tangent line. Seem reasonable? Now, I'm going to cheat a little bit. I'm even going to tell you which questions I'm going to cheat with. Questions 4, question 5, question 8, and question 11. Any more? That's it. For these 4 questions, we're going to cheat, but in a nice way, a mathematical way, not just look at the answer and write it down kind of way. I am going to show you a shortcut for finding f dashed of a. the slope of the tangent line to a curve, right, at x equals a. And I'm only going to show you the shortcut for polynomials, right? X squared, x cubed, guys, right? I'm not going to show you it for square roots because I want you to get good practice at them. And I'm not going to show you it for fractions because you really need some practice at those guys. But eventually I'll show you the shortcut for them as well. But that'll come in a different section. So here is, we're going to pretend, I guess that's a good one. We are going to pretend that we are the first mathematicians to do this, right? We created, like Newton and Leibniz, so the guys that did it, we created all this to find slopes of tangent line. And 3x squared plus 4x. And we got the answer. And, oops, and the answer is 6a plus 4. And when f of x was 10x cubed, the slope of the tangent line of a, f dashed of a, was 30 a squared. And when it was x squared minus 10x plus 3, the slope of the tangent line was 2a take away 10. And when the function was 5x cubed plus 4x squared minus 2x plus 1, the slope of the tangent line was 15a squared plus 8a take away 2. And one of the things mathematicians love are puzzles and patterns. These answers are not random. There is a pattern that this guy can be used to generate the answer. Can anybody see a pattern from how you can go from here to here?
You're multiplying the coefficient by the square number in most of them. That makes sense.
Okay.
Like the 3 times 2 gives you the 6a in the first one, and then you're dropping the x in the second value.
Right, and what happening here? That makes sense what you just said, Kelsey.
Mm-hmm.
What happens here in the x cubed version?
You just drop the square value or the cubed value to a square value. So you're like removing an x each time you do it.
Right, so you remove, yeah.
Okay. I noticed it a while ago and I was like, I wonder if that's a real thing.
Well, you're doing the same process that I'm sure the first people who did it were doing. Hey, that was a lot of work. And then you do a lot of them and you say, wait a minute, there's something going on here.
Mm-hmm.
And what's going on here has got a name. And what you said is totally correct. And this name is called the power rule. And what it says is, so I'm going to go through these and basically just paraphrase what you said. I'm not changing what you said. I'm just saying it maybe in a different way. See this guy here? To get the answer, multiplied by the power. So 2 times 3 gets you 6, and then reduce the power by 1. So 6x becomes 6a. Technically speaking, isn't that 4x to the power of 1? So you multiply the power and the coefficient together, so that's 4, and then you reduce the power by 1. What is x to the 0? 1. So that's why you end up with 4. Right. Multiply by the power, 30x squared. 30x squared becomes 30a squared. X squared becomes 2x. It turns into 2a. Negative 10. X turns into just negative 10. 5x cubed plus 4x squared, this guy here. Multiply by the power, do you see a 15x squared? Turns into 15a. 8x, 8a, minus 2x, gets you -2. And do you notice that the numbers, the +3 and the +1, just totally disappear? Right? And if you were using the power rule, you could think of that as 3 times x to the power of 0. And what happens if you multiply by the power? Well, 3 times nothing gets you nothing, it disappears. So it's technically still the power rule. I just think of it as if there's a constant that disappears. Now, if that, and it is correct, we should be able to do this guy.
The X's just turn into A's, right?
Yeah. And later on, the A's turn back into X's and we'd stop using the A's completely. Okay, here is a ridiculous polynomial. If you had to do that as h tends to 0, would you agree you'd be here for a fair amount of time? Right? Be a very long question. I'll take a volunteer. Anybody want to do, well, we'll do different volunteers. Take a volunteer for the first one. What will 10x to the 5 get you in terms of A?
50A.
And to what power?
1, I guess.
Not 1.
Well, don't
Multiply
you-
by the, and then you reduce it by 1.
Oh, okay.
Right.
Maybe that's where I was confused. Okay.
Okay. Next one. What are you going to get as the coefficient? What number will I get first?
-12.
And what power
Wow.
of A will I now get?
2.
So, do you see the power reducing by 1? Do you see the coefficient being what you get when you multiply the original power by this number? So, based on what I've just said, then, wouldn't this one be 2 times 10 is 20, and then reduce the power by 1? I like to think of 4x as a special case. Doesn't that just get you 4? And what will happen to the number -1? Disappears, right? Has no effect on the answer. It's kind of cool, isn't it? No shortcut. So, here is a question that we did earlier today. Right? Let's use the power rule on it. What is going to be f dash of A? Multiply by the power and reduce the power by 1. 3x gets you 3. What about the -1? Disappears. And the answer is 4a plus 3.
Does this rule work with all the equations we've been doing?
You have to only, this rule is only going to work for polynomials, right? 5x cubed, 4x squared. Don't try and use it with square roots, and don't try and use it with fractions.
Okay.
It just ain't going to happen. We have other shortcuts for those guys, right? We have other rules that allow us to do those types of things. Do you like this one? Do you like this shortcut? Right?
Yeah, I have a quick question about
Yeah.
the square roots.
Mm-hmm.
Since they're technically 1/2 as far as exponents go.
Yeah.
That then be, you could times it by 1/2.
You'd have to adapt it a little bit, but yes. And the reason you have to adapt it is it could be the square root of 4x plus 3, or something like that. And when it's something like that, there's adaptations, and we're not going into those yet. That will be shown to you, right? Later on, we'll show you how do you deal with all the other functions in the world that you don't want to do the long way, right? There must be a way to find them. And we spend quite a lot of time looking at different ways to find derivatives of functions. This one is the first rule that you learn. It's called the product rule. Later on, you're going to find other rules. quotient rule, product rule, chain rule, implicit differentiation, logarithmic differentiation. I think I've covered all the obvious ones. So there are going to be lots of different strategies for different circumstances. Like, how do you differentiate the square root of 4x plus 1, right? There'll be a method, right? I'm calling them shortcuts, but essentially there'll be methods that you can use to do those. What about 1 over x squared plus 1? There'll be methods for doing that. There are even going to be ones for sine x and trig functions, and e to the 2x, and all sorts of other cool stuff. So we're going to spend a lot of time figuring out how to find derivatives. And we have reached a very natural stopping point. So say hi. Is your kid Kelsey want to join in? I think she was desperate to tell us something. You want to put her on now and I'll say hi.
He just told me to put 2 + 2 = 4. You want to say hi? I'll say hi to you. Come here. No? Now he's being bashful.
Oh, well.
I'm sorry.
See, the next time you want to be quiet, just tell them to come on and talk to me and they'll shut up right away.
Yeah.
Yeah, you never thought of that, did you? Okay, bye. Hi and bye-bye. I'll hang about if there's any questions.
Thank you. Have a great weekend.
If you have 2
intend to.
polynomials,
Yeah, if I don't turn up on Tuesday, it's because I'm in jail.
All right. Mental note made.
so I have a question.
Yes, Teresa.
So if you have 2 polynomials that look just like that one, but one's divided by the other, can you just do this twice on the once on the top?
No, I wish
bottom?
you could. No, you have to do a different rule, and it's called the quotient rule when that happens. No,
Okay.
I wish this rule was the only rule you needed. It would make calculus a lot easier than it is, because you have to use different techniques, different rules as they're called, for different circumstances. So what you were talking about there would be a quotient rule, would be the rule that I choose. In other questions, you use a chain rule or something instead. Depends on, what you've got to start with. Kind of dictates what technique you're going to use to find its derivative.
Okay. And then my other question is when you have a tangent line and you find the slope of it, I'm a little confused with, like, is that a velocity or whatnot?
Well, it can be. It can just simply be geometry. It could simply just be the equation of the line that is the tangent line. Right. So if you had a curve and you drew it, and you were interested in the tangent line at x equals 3, the equation of the tangent line is just the equation of that line, right? The line in 2D space. It would just be pure geometry. If the function you started with was a position function, like s of t says where you are,
like that.
when you do something like that, then the velocity is what the derivative is. In other words, finding the derivative is the equivalent to finding the velocity at a given point.
But I can't understand is if you jump off a cliff or something, it seems like the velocity equals the change in distance over the change in time. Yeah. I should just get a straight velocity for that, but then...
Well, not really, because gravity takes over. So at different points, your velocity changes. When you don't do this, but if you jumped off a cliff at the beginning, you might only be going at 1 meter a second. Yeah. But when you hit the rocks at the bottom, you could be going 100 meters a second. Right, so your velocity is going to change.
So is the tangent line doesn't tell me, does it tell me the change? It tells me any point along there how fast I'm going?
Yeah, because in the case of that situation, the derivative is the velocity. So it is telling you that. I mean, so if I was, I'm trying to draw a little picture of what that might look like. If I was doing a story about, why can't I find things when I want them? Here we go. If we were doing the throw off the cliff one, right, that might be the pathway, right? So you got a rock and you chucked it up and it went up and then it came down. At this point here, the slope might be 2. That means you're going upwards at 2 meters a second. At this point here, the slope is negative, so that might be -5. Here it might be a little bit steeper, -6, and then when you finally hit the ground, it might be -7. As you travel from here all the way around to here, the slope of the tangent line, that number that represents the slope, is telling you the velocity at any given point. That's just one of the applications, right? So if you're talking about, oh, I know that this function is telling me the position of an object at time t, then the derivative at a is telling me the velocity when time is a. So it is doing that. For instance, in this question here, at that point there, right at the top of the hill, wouldn't the tangent line be a horizontal line? And a horizontal line has a slope of 0. So at that one point on the journey of this rock, as I throw it up and then it comes down and hits the sea down here, at that one point there, for an instant of time, isn't that rock stationary? In cartoons, they emphasize that. Have you ever seen the ones where they jump off the cliff and then for like a second they're wiggling their little legs and then they hit the ground? Well, that's an extended version of reality, right? For a microsecond, you're technically stationary, but then you're going to start moving. In different setups, the derivative can tell you different things. The way we describe it as that the derivative can be thought of as a rate of change. So if you take the rate of change of position over time, that's called velocity in physics. But what do you do if you take the rate of change of velocity with time? That's called something as well, isn't it?
Acceleration.
Yeah. So if you gave me a function that told me the velocity of an object at any given point in time, if I found the derivative, right, the slope of the tangent line, I'd be telling you the acceleration of that object at that point in time.